Here we go with example 6. Let's put the Riemann sum into action. Okay, so we can see that we have the function y equals, or f of x equals x squared. And there's our graph right there. If you want to take a moment and actually create this graph on your paper, that might be a good idea just to help you visualize what's happening here. Okay, now we're looking to find the area of the region under the curve from x equals 0 to x equals 2. All right, so we're focusing on this region right here. Okay, and how are we doing it? How are we going about it? Well, we're going to use the Riemann sum. We're going to do left and right. We'll take a look quickly at the midpoint as well. And we want to use, we're told, according to the problem, 4 equal subintervals. All right, so we got to go from 0 to 2. That's 2 units. We got to break it up into 4 subintervals. All right, so 2 divided by 4 means we're going by a half a unit each. All right, so half a unit, and then another half unit gets us to 1, another half unit gets us to 3 halves, and another half unit gets us to 2. So I'm going to draw the verticals here, all right, so that we can kind of see what's happening. All right, there's our 4 subintervals. Okay, and we want to find the area of the 4 rectangles that we're going to create. So let's start with the left sum. All right, so if it's a left Riemann sum, that means the upper left-hand corner of our rectangle is going to touch the curve. Now, the curve the first time around on the left side of this first rectangle is actually at 0. Okay, so we don't really even have a rectangle, we just have a line. Okay, the second rectangle, its upper left-hand corner hits right when x is equal to a half. Okay, and y happens to be a quarter, because if we take a half and we plug it into the function, all right, you always get a y value by plugging the x value into the function. So a half squared is a quarter, right? 1 squared is 1, 3 halves squared is 9 quarters, and then 2 squared gives us 4, right? But we're going to have our upper left corner touch in each of the 4 subintervals, okay? And again, in that first subinterval, we have no area because the base, even though it's a half, and in fact the base is always going to be a half, all right? So on and so forth. The base is a half, but the height is 0. So for our first rectangle, when we're finding the area, it's going to be 1/2 times 0, all right? The base is the distance between the x values. So the distance between 0 and a half is a half unit, and the height is the function's value at the point we're interested in. We're interested in the left endpoint. The left endpoint is 0. 0 squared is 0. That's why we have a 0 right there. Okay. Let's go to the second rectangle. Here's our second rectangle right here. Kind of a small one. Okay, let's shade that in. Okay. All right, what's the base? Well, once again, the base is a half. Okay, this time the height is this high up. Well, the function touches the rectangle on the left side when x is equal to a half. A half squared we know is a quarter. So when we find our area, base is a half, height is a quarter. And again, this quarter comes from taking the x value and punching it into the function. Our third rectangle, all right, right here, again, base is a half a unit, and the height is the value of the function on the left endpoint. 1 squared is 1. So we're going to have 1/2, that's our base, times our height, which is 1. And then for our last rectangle, okay, our base is a half, as always in this situation, and the height is our function's value at 3 halves, which happens to be 9 quarters. So we have a half times 9 quarters, okay? Now, the 2 doesn't get used when we do the left sum. It will get used in the right sum. Hold off 1 second on that. Let's calculate our area real quickly here. So we have 0 plus 1/8 plus a half plus 9/8. All right, now we know that a half is actually 4/8 if we just write the equivalent ratio. So we have 0/8 plus 1/8 plus 4/8 plus 9/8, so it's a total of 14/8, which we can think of also as 1 and 6/8 if you prefer. 6/8 is 3/4, so this is 1 3/4 or 1.75. Right? So that's an approximate area of the region under the curve. And obviously it's wrong. Obviously it's just an estimation. Okay, but that's okay because it's an estimation. It doesn't have to be exact. Right? We're missing this zone here, we're missing that zone there, this zone, we're missing a lot of stuff. So this is definitely too small. Let's take a look at what happens when we do a right Riemann sum. All right, when we do a right Riemann sum, now the upper right-hand corner of the function is going to touch the curve. So what ends up happening is we get these 4 rectangles. The upper right-hand corner of each rectangle is touching the curve. When I fill in these values now, we can see that we have way too much area that we are accounting for. But again, that's okay because it's just an approximation. But with this approximation that we do get, it's going to be too large. Well, what happens? I don't know if you noticed, but every single rectangle kind of just shifted over one slot. All right, this rectangle that was here for the last one just got moved over. All right, we have a base of a half and a height of a quarter. Right, base of a half, height of a quarter. Except now instead of it being our second rectangle, it's our first rectangle. Half times a quarter. The second rectangle we can clearly see has a height of 1, as did our third rectangle in the first part there. So we have base times height. And then we're going to have base again times height. And our third rectangle has a height of 9/4. And our last rectangle always has a base of a half and a height this time of 4. Okay, so when we put all of this together, we end up having an eighth plus a half plus 9/8 plus 2. Well, an eighth plus a half plus 9/8 is 1.75, but we're going to add 2 to that. So this is going to come out to be 3.75. Okay. So the left and the right sum are rather easy to calculate. The midpoint sum is a little bit more difficult. It's much more accurate, but now what we're looking at is the middle of each rectangle touching the curve. So some of the rectangle is going to be above the curve, and some of it's going to be below the curve. Let me do this one right here. Right, we can see here and here. So we have this space right here, which is above the curve, but then we're also missing that little almost triangular type space right there. Okay, same thing happens with the next one as well. Okay, our midpoint is somewhere in that vicinity. So we have this region. We're missing this region, but we have a little bit extra right there. Okay, now to get the midpoint values, the bases are still going to be the same. The base is going to be a half. But now we need the height, and the height is in between 0 and a half, or in between a half and 1. So we're looking at a quarter and 3/4. And this one will end up being 5/4, and then we have 7/4. All right, so what ends up happening is when we plug a quarter in here, we end up having a 16th. 1/4 squared is a 16th. And we have base. And our next height will be 3/4, all right, or 9/16. All right, and then our next one will be base is a half, and our height is 25/16. And then the last one will be a base of a half and a height of 49/16. Okay, so now this answer that we've got right here is not simplified, but it is correct. And we can take a moment and use a calculator to come up with a value, but this value right here is going to be much, much closer. All right. It turns out that the actual value is 8/3, or 2.6 repeating. All right, so we can see that 1.75 was off by a lot, 3.75 was off by a lot. This one comes out to be much, much closer to 2.6 repeating. And again, just calculate that on your calculators there. But the midpoint is definitely the most accurate of the 3. And as we mentioned in the previous video, what's even better is instead of doing 4 subintervals, what if we were able to do 40 or 400 or 4 million or 4 billion subintervals? Now it would take too long to calculate by hand, but we can let the calculator do the work for us, and that would get us an answer that, if we can get just enough rectangles, an infinite amount of rectangles, would actually give us the exact value of 8/3.